to understand one of the most counterintuitive ideas in environmental science. We need to travel back to 1865, the height of the Victorian era. Great Britain was the workshop of the world, its empire expanding, its factories humming, and the Royal Navy ruling the waves. And everything, absolutely everything, depended on one black rock: coal. Coal powered the steam engines, smelted the steel, and heated the homes. But in the scientific societies of London, a panic was growing. Geologists had done the math and warned that Britain's coal seams were not infinite. Mines were getting deeper, and extraction was becoming more expensive. The fear was real. If they ran out of coal, the empire would grind to a halt. It would be a return to the Stone Age, but then the optimists stepped forward. The engineers and technocrats of the 19th century offered a solution. "Don't panic," they said. "We're inventing better machines." They pointed to the amazing evolution of the steam engine. The early engines were terribly inefficient, wasting almost all their heat. But the new engines, perfected by James Watt and his successors, were marvels of efficiency. They could do the same work using just a fraction of the coal. The logic seemed flawless. 1. Our engines are more efficient. 2. Each engine burns less coal. 3. Therefore, the nation's total coal consumption will drop. And 4. Our resources will last longer. It's a comforting thought, the same logic we use today when we buy a hybrid car or an energy-saving light bulb. But in 1865, a 29-year-old economist named William Stanley Jevons published a book that shattered this optimism. The book was called The Coal Question. In it, Jevons made a prediction that seemed insane at the time. He argued that making the steam engine more efficient would not reduce coal consumption. It would increase it. He argued that the more efficient we become, the faster we will burn through our resources. He wrote, "It is a confusion of ideas to suppose that the economical use of fuel is equivalent to diminished consumption. The very contrary is the truth," and history proved him right. In the decades that followed, Britain's coal consumption didn't fall. It skyrocketed. This phenomena is now known as the Jevons paradox, and it explains why, despite 50 years of energy efficiency policies, the world is consuming more energy than ever before. So, why does this happen? Why does saving lead to more spending? To understand the Jevons paradox, we have to stop thinking like engineers and start thinking like economists. An engineer sees units of energy, an economist sees cost. When using a resource is inefficient, it's expensive. Think of those early steam engines. They consumed so much coal that they were only profitable to use right next to a coal mine. It was simply too expensive to haul tons of coal to a distant factory to run a bad engine. So the demand for steam power was limited by its own inefficiency. But when James Watt increased the efficiency, he effectively lowered the price of steam power. Suddenly, steam became cheap. And because it was cheap, it became portable. Now, you could put a steam engine in a factory in Manchester. Then you could put one on wheels to create a locomotive. And you could put one on a ship. The cost of power dropped, so the number of applications for that power exploded. Jevons realized that efficiency acts like a subsidy. The savings from using less coal per machine were completely overwhelmed by building thousands of new machines. We didn't use the efficiency to save coal, we used it to power the entire industrial revolution. In modern economics, we've refined Jevons' idea into something called the rebound effect. It explains why our personal energy bills rarely go down, even when we buy better technology. It happens in 3 stages. First is the direct rebound effect. Imagine you buy a new car. Your old one got 20 miles per gallon. Your new hybrid gets 50. Technically, you can drive the same distance for less money, but do you? Probably not. Because driving is now cheaper, you drive more. You decide to take that road trip you've been putting off. You start commuting from a nicer house further from the city. You take back some of the efficiency gains by consuming more of the service, which in this case is miles driven. Second is the indirect rebound effect. Let's say you're very disciplined. You buy the hybrid and drive the exact same number of miles, saving $1,000 a year on gas. Great. But what do you do with that extra $1,000? You spend it. Maybe you buy a plane ticket for a vacation. Maybe you get a new smartphone or eat out more. All of those things, flights, phones, restaurants, require energy to produce and operate. The energy you saved at the gas pump is simply transferred to the airline industry or the tech industry. Your personal carbon footprint might shift, but the total economy's energy use doesn't necessarily go down. Finally, there's the macro rebound, or what we call a full backfire. This is the Jevons paradox in its purest form. The new, more efficient technology makes society as a whole more productive. A more productive society grows faster, and a growing economy consumes more resources. Ultimately, efficiency is the engine of growth, and growth is the engine of consumption. The most visual example of this in our lifetime is light. For thousands of years, light was a luxury. A candle was precious, whale oil was expensive, and the first incandescent bulbs were incredibly wasteful. Because light was expensive, we treated it with respect. We turned off lights when we left a room. Streets were dim. Then came the LED. The invention of the blue LED, which won a Nobel Prize, revolutionized lighting. An LED uses 90% less electricity than an old bulb to produce the same amount of light. Governments banned the old bulbs, promising this would slash global energy demand for lighting. Did it? According to satellite data, the artificially lit surface of the Earth has grown by over 2% per year since LEDs were introduced. We didn't use the efficiency to save electricity. We use it to conquer the night. Because light is now almost too cheap to meter, we use it frivolously. We have decorative lights on bridges that stay on all night, giant digital billboards brighter than the sun, and glass skyscrapers lit from top to bottom, 24/7s. We consume the efficiency gains in the form of more light, not less electricity. We are drowning in light because light became cheap. Consider air conditioning. In the 1970s, AC units were loud, energy-hungry beasts. Only the wealthy in hot climates had them. Today, AC units are incredibly efficient, using half the energy of a model from the 90s. So has energy use for cooling dropped? No, it has exploded. Why? Because AC became cheap enough to install everywhere. Now, 90% of homes in the US have it. But more importantly, efficient AC allowed people to move to places that were previously uninhabitable for large populations, like Phoenix, Las Vegas, and Dubai. The efficiency of the air conditioner enabled the construction of massive cities in the desert. Those cities now require billions of kilowatt hours just to stay cool. If AC had remained inefficient and expensive, Phoenix would still be a small town. Efficiency enabled civilization to expand into the furnace, drastically increasing our total energy load. The most urgent modern application of the Jevons paradox is in computing and AI. We have Moore's law, which states that computing power gets cheaper and more efficient every year. A modern graphics card is millions of times more efficient per calculation than a 1990s computer. If Jevons was wrong, our data centers should be running on tiny batteries by now. But Jevons was right. Because calculation is cheap, we invent new, incredibly wasteful ways to use it. We invented Bitcoin mining, a process that intentionally burns electricity to secure a network. We invented generative AI. Training a single AI model can consume gigawatt hours of energy. Every time you ask an AI to write a poem or create an image, huge server farms heat up. We are building data centers that consume as much power as small countries. Why? Because the chips are efficient enough to make it possible. If computers were still powered by vacuum tubes, large-scale AI would be impossible, and our energy consumption from computing would be far, far lower. So what does this all teach us? It's a hard pill to swallow for techno-optimists. We love to believe that green tech will save us. We think if we just make our cars more efficient or invent fusion energy, our problems will be solved. Jevons tells us no. Innovation is an accelerator, not a brake. Efficiency lowers the cost of an activity. And when something is cheap, humans do more of it.